Hi guys, I hope everyone's doing well. You can see me now, so that's exciting, right? So we're going to do chapter 14, part 2 today. Last time we went over the difference between spontaneous generation and biogenesis. And if you guys remember, spontaneous generation was non-living things can give rise to living things. And we finally negated that and we accepted biogenesis, saying that living things have to come from other living things. Now, given that, if spontaneous generation is invalid, then how did the first things come to be on Earth? And that's kind of what we're going to talk about over the next two videos. So just to start off, just to give you a little bit of a overview of Earth, we think that in order for Earth to be here, we had to have the sun first. And we think that the sun came about 5 billion years ago. All right, that's a few days ago, right? No, a long time ago. And what we think happened was that there was a lot of gas and dust out there. And all of this, because of gravity, it came together and formed our sun. Okay, so there's our sun, just a big ball of gas and dust. And there was Superman. I don't know where he came from. But anyway, so after we had the sun, we still had some dust and debris out there that couldn't quite get pulled in to the sun. In other words, it couldn't get pulled into its gravity. So this process repeated, and that's how we ended up with our planets, with whether it's Earth, Mars, so on and so forth. So it took a long time for Earth to grow as big as it was today, and it wasn't stable to harvest life when it started to get all this debris, and when that debris started to come together. I got a little video for you guys on this. It's a really cool video. It's Earth in 4K, just to show you like the oceans and all the land on Earth. And I'll post that on Google Classroom for you guys if you want to watch it. So we estimate Earth to be 4 billion years old. So if you guys remember, we just talked about the sun. The sun was 5 billion years old. The Earth is 4 billion years old. That means that from the time the sun became, in existence, I guess, it took 1 billion years for Earth and a lot of the other planets to come into existence, right? How do we know this? Well, we take this number because we think that radiometric dating through different isotopes and things like that, and we'll go over that in a few minutes, but we think they're able to give us a good date on how old Earth really is. So here's a little review from chapter 2, long time ago. This was the chemistry chapter, but we have protons, neutrons, and electrons, all right? And we have a mass, atomic mass, or a mass number, whatever you want to call it. That's our number of protons and our neutrons, and these are like the main subatomic particles of our atom. So the protons and neutrons, they're very large, and the electrons, they're very little. And if you guys remember, if this is our nucleus, they circle all around everything. But the atomic number is never going to change, so our number of protons is never going to change. But our number of neutrons, that can change. And when that number changes, we have things called isotopes. And that's what we're going to talk about. And I know we talked about it in chapter 2, but I'm sure, guys, with everything going on, you need a little refresher on that. All right. So there are 3 different isotopes here of carbon. We have carbon 12, carbon 13, and carbon 14. I showed you the same picture in chapter 2. Carbon 12 has 6 protons, carbon 13 has 6 protons, and carbon 14 also has 6 protons. Well, what's the difference between them? The difference is our number of neutrons. Carbon 12 has 6 neutrons, carbon 13 has 7, and carbon 14 has 8. So that's the only difference between our isotopes. So isotopes have the same exact number of protons, it's the same element, but the difference is the number of neutrons. And that difference in the number of neutrons doesn't change the atom. It's still the same atom. It's still carbon in all this. All right. Some of our isotopes, especially like carbon 14, they are radioactive and they're not stable. So what happens is these isotopes, they're going to decay over time. And when they decay, we can have carbon 14 actually become carbon 13. It just takes a long time for that to happen. All right. So what happens whenever they are going to lose some of their weight? It's called a half-life, and atoms do decay over time, guys, okay? Everything in the world is pretty much like, you think of the water cycle, you guys drink water, that water comes out, that water, at some time, the parts that is water, evaporates, goes up into the sky, and then the clouds will rain it back down on you. Kind of gross to think about it. But anyway, um, different half-lives, in other words, the time it takes for an atom to decay by half could take, hardly any time at all, but it could also take a very, very, very long time, like billions of years. Our bodies, guys, we're mostly made up of carbon. Carbon's our main, we are like carbon-based organisms. And whenever we die, the carbon in our body, it's no longer going to be, I guess, taken in and given out because we stop digesting things and we stop, giving off things. But the carbon is still going to decay over time because the carbon isn't living. The carbon is just an atom. The half-life of carbon is 5,730 years. So if we took the carbon in your body after you're dead, we can kind of set a date with how old you are if we found your remains like way, 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 way down the line. Just by seeing what state the carbon is. Is it carbon 14? Is it carbon 13? Is it carbon 12? How close is it to carbon 13? How close is it to carbon 12? So it's kind of cool with half-lives. If you look at this carbon 14 right here, we have a little graph. And what happened here, guys, is it started off with 100% of carbon. And they had a sample of carbon that was 10 grams, okay? Every single half-life, we're losing half of that, okay? I know when I was in school, I always had trouble with half-lives. My teacher didn't explain it real well. So here's it very simply. Pretend we have 10 grams of carbon, and we're not even going to say how long a half-life is of carbon right now. But if we have 10 grams of carbon, after one half-life, we're going to decrease that amount by half. So if we have 10 grams, after one half-life, we now have 5 grams, okay? So after one half-life, we have 5 grams. If we go to 2 half-lives, so the first half-life got rid of 5 grams. Now we have 5 grams, and we're going to decrease that by half again. So after 2 half-lives, we're going to have 2.5 grams. So pretty much all we're doing is dividing the number by 2 each time. So 10 would go to 5 after one half-life. The 5 would go to 2.5 after 2 half-lives. And then the 2.5 would go to 1.25 after 3 half-lives, okay? So that's how you estimate how much would be left after a given number of half-lives. Here's a little example for you guys. If we have 1 gram of some radioactive isotope and the half-life is 1 billion years, how much of it would be left over after each of the following? So if we have 1 gram, after 1 billion years, we're going to have half of that amount. So it's going to be 0.5 grams. After 2 billion years, well, that's 2 half-lives, so that 0.5 gets reduced in half again. It's going to be 0.25. After the next half-life, decrease it in half again, 0.125. And then for the last half-life, it would be very, very small, 0.06, okay? But you can see all we do is decrease it by half each time. Here are some half-lives for you, okay? You can see the carbon-14 has a very small half-life. It's 5,730 years. But if we go to uranium or potassium, those ones have much longer half-life. So if we have a sample of uranium-235, it's going to take 704 million years for that to decrease by half, okay? Long time. So this brings about the question with dinosaurs, yeah. So we know that the dinosaurs lived, over 60 million years ago. I don't think this is a good picture from 60 million years ago. Let me try a different one. I don't think this one works either. But here's a dinosaur jump roping. Okay, wait, let me get something a little more factual, what it might look like at the time. There we go. Okay, so dinosaurs, over 60 million years ago. If we were to use a half-life of carbon to estimate the age of dinosaurs, it's probably not going to be real well because the half-life is only 5,700 years. The carbon's going to be so small if we go for over 60 million years ago that we may not have a very big sample and it's going to be hard to estimate it. So what they did, guys, whenever they were estimating the age of the dinosaurs, they actually found its fossils and went to the rocks that were surrounding the dinosaurs' fossils, and they estimated the dates of the rocks around them. And in estimating the rocks, that's how they estimated the dinosaurs. So instead they use like uranium or potassium as the sample for the half-life for dinosaurs. Okay, so one more example, guys. Uranium-235. Okay, so uranium-235 or 238. It has a half-life of 4.5 billion years. 4.5 billion years. Okay, so originally we had 40 grams. Okay, so we had 40 grams. Okay, now after one half-life, so one half-life here, which would be 4.5 billion years. 4.5. Sorry, not great with the pen, guys. We'll just say B for billion. After 4.5 billion years, that 40 grams is going to be cut in half. So that's one half-life. So now after 4.5 billion years, we're going to have 20 grams of our uranium-238. Okay, so that's one half-life. How much of this would be left over after 9 billion years? So we already did 4.5 billion. We got to do that one more time. Okay, so another 4.5 billion years goes by. So after two half-lives, or 40 billion years, we're going to have 10 grams left of our uranium-238. Okay, so that's pretty much with half-lives, guys. That's all you really need to know.